Now that we've learned about the Opirus automatic transaxle, let's move on to the chassis system. The ECS system used in some Opirus models is an electronic controlled suspension. The ECS improves the vehicle's ride quality from handling performance by controlling the vehicle's motions depending on road surface conditions and the driver's actions. This video shows the shock absorber damper characteristics of the electronic controlled suspension system, how ECS controls the suspension, and inputs and outputs. First of all, let's see the damper characteristics of the semi-active ECS system. A proportional solenoid valve is attached to the bottom of the shock absorber on ECS systems. Damping characteristics are changed based on the amount of current supplied to the solenoid. The amount of current applied to the solenoid controls the rotation of the pilot spool valve inside the shock absorber. The spool valve controls oil flow, altering compression and rebound field. When applied current is 0.3 to 0.8 amps, the damping force in the compression stroke becomes soft, but damping force is hard during the rebound stroke. When the applied current is 0.8 to 1.3 amps, the damping force in the compression stroke becomes hard, and damping force is soft during the rebound stroke. When the applied current is 0.8 amps, the damping forces are soft in both rebound and compression conditions. Now, let's move on to the ECS control. The ECS system controls the vehicle's ride and handling. Ride control consists of controlling the vehicle's action during anti-bounce, anti-roll, and anti-pitch situations, and sensing road conditions such as bumpiness or smoothness during road judgment control. Ride control related to the vertical motion of the vehicle is regulated by the information from the vertical acceleration sensors as well as the vehicle speed sensor. As for the control related to the handling, there's an anti-roll control, anti-dive control, anti-squat control, and speed-sensitive control. The anti-roll control uses the steering angular velocity of the vehicle's speed. Anti-dive control uses brake on-off information and the vehicle speed signal, and the anti-squat control uses the TPS signal. Besides, the speed-sensitive control begins to apply when the vehicle speed is over 140 kilometers per hour, providing the hard damping force. Now let's learn about the ECS inputs and outputs. These are the primary inputs for the ECS. The alternator L terminal senses the alternator is generating enough power to run the ECS components properly. A brake switch to control the anti-dive. An ECS select switch to choose between normal and sport modes. Normal mode provides a comfortable ride, and the sport mode stiffens the suspension for better handling. A vehicle speed sensor for overall handling control. A steering sensor for anti-roll control. A TPS for anti-squat control. And 3 acceleration sensors for overall ride control. These are the primary outputs. An ECS indicator used as a warning lamp. An actuator relay which supplies power to the solenoids. And 4 solenoid valves which controls the damping force of the 4 shock absorbers. Let's look at the structure of the solenoid valve. The solenoid consists of an inner coil, spring, plunger, spool valve, and dampening control valve. 2 springs are located at both ends of the plunger and spool valve. Depending on the current applied to the coil, the spool valve may be moved by the springs. In this example, the spool valve moves to the left. Now let's see how the oil flows based on the position of the spool valve. When the applied current is 0.8 amps, the damping force is soft for both compression and rebound strokes. At 0.8 amps, the spool valve passageways are both open. The oil inside the rebound and compression chamber flows easily to the base chamber through the spool valve. When the applied current drops below 0.8 amps, the spool valve moves to the left as the force of the spring against the spool valve overcomes the dropping magnetic force of the coil. During the compression stroke, the oil flows from the compression chamber to the base chamber freely because the spool valve remains open. As a result, the compression stroke remains soft. As the spool valve moves left, the opening for the rebound chamber to the base chamber gets smaller, restricting oil flow. When applied current reaches 0.3 amps, the oil path is closed completely and the rebound stroke becomes the hardest. If the applied current increases above 0.8 amps, the spool valve moves to the right, decreasing oil flow to the compression chamber. When current increases to 1.3 amps, the opening between the compression chamber and the base chamber is closed completely. At 1.3 amps, the compression stroke becomes the hardest. During the rebound stroke, the oil path from the rebound chamber to the base chamber through the spool valve remains open, so the rebound stroke remains soft. We have reviewed the semi-active ECS system used in the Opirus. Now let's move on to the ESP. The ESP provides improved driving stability relative to under and oversteer conditions. Further, the brake assist system, or BAS, is added to supply just the right amount of braking during these conditions. To better understand the ESP system in the Opirus, we'll explain about the ESP control module, inputs and outputs, and a brief introduction of the BAS. Let's look at the functions of the ESP control module now. The ESP control module is integrated into the ESP unit. It continuously monitors all electrical components and provides diagnostic help. The ESP control module helps maintain vehicle stability by effectively controlling understeer and oversteer. It also controls ABS and TCS functions. Let's study how the ESP controls the vehicle during understeer and oversteer conditions. Understeering. The vehicle does not steer as much as the driver intends, begins while the vehicle is turning. The vehicle slips outward, away from the direction of the turn, regardless of the driver's intention. Now, understeer control starts. The ESP control module generates braking force at the inner wheel of the turn. The inner wheel pulls the vehicle towards the circle, correcting for understeer. On the other hand, if oversteering occurs while turning, the vehicle moves toward the direction of the turn too far. Now, oversteer control starts. The ESP control module generates braking force to the outer wheels. The braking action on the outer wheels pulls the vehicle away from the circle, correcting for oversteer. Now, let's review the inputs and outputs. The inputs of the ESP system are 4 active type wheel speed sensors, a steering angle sensor, a combination yaw rate and lateral acceleration sensor, 2 pressure sensors, a brake switch, and ESP off switch. As for the outputs, there's a motor pump, solenoid valves, ABS warning lamp, EBD warning lamp, TCS and ESP warning lamp, TCS and ESP function lamp, and CAN communication line with the power control module, or PCM. Now let's take a look at the new ESP wheel speed sensors. These new sensors are an active magnetic resistance type. When powered by 12 volts, the sensors generate 7 milliamps or 14 milliamps. The wheel speed sensor is located on the hub, and the air gap cannot be measured because of the sensor's protection cap. The ESP control module calculates the vehicle yaw rate based on the steering angle sensor signal and other inputs while turning. The calculated yaw rate and the actual yaw rate from the sensor cluster are compared together. The difference between the two valves is the basic factor to determine the vehicle's understeer or oversteer condition. The lateral acceleration sensor and the yaw rate sensor are important components of the ESP. The cluster links these sensors to an onboard computer unit, and to a CAN interface. The sensor cluster is mounted on the chassis under the center console. Its modular design concept allows future additional sensor functions. The pressure sensor shows the driver's braking intentions. When the brake pedal is not applied, the output voltage is 0.5 volts. And when the brake pedal is applied, the output voltage increases to nearly 4.7 volts. Let's learn about the BAS, Brake Assist System, used in the ESP. The BAS used in the Opirus ESP has extended logic to assist braking by driving the ESP hydraulic unit on demand. To operate the BAS, the following three conditions must occur at the same time. Braking pressure should exceed 20 bar, and pressure increase rate is more than 1100 bars per second, and the vehicle speed exceeds 7 kilometers per hour. When the BAS control logic recognizes that there's an emergency braking situation, the shuttle valve is opened and the TCS valve is closed. The ESP pump starts up and increases the braking pressure in a split second to a pressure level above the current driver-applied level. The ABS then keeps the individual wheels from locking up.